We're going to be modeling these quadratics in this section, and what we're doing, a lot of times the modeling is just word problems, but what we can do is we can also use them to predict and try to see. The word optimize is also used when we're talking about like the highest or the lowest optimization. And don't be scared, a lot of times they give you the equation. Now, the reason why this equation should make sense is gravity is going to constantly pull something back to Earth. So whatever this object is that's going up, it has to have a speed going up. So that's where this 112t comes from. But then gravity is going to pull it back to Earth. So if you're talking about at what height was the object fired, I almost gave that answer away, because if you're just firing it, that means that t equals 0. So basically I'm asking you to find out what h of 0 is, which shouldn't be too bad. You don't even need a calculator for it, because anything times 0 is 0. And if you were good with units, you would want to say 0 feet, because feet per second, they give you that in the directions. So as far as a general curve goes, all I know is that at the origin, it's going to be where it starts, goes up into the air, and then comes back. So this would be the time axis. This is the height. It even tells you that. You can write down the units and things like that. So that's just the general curve on this problem. And you can even put the 0, 0 in right here. But then we can algebraically find the time the rocket reaches its greatest height, which is also its maximum height. And the way you would do that is by doing the formula we talked about, negative b over 2a. So as a reminder, a is equal to negative 16. B is equal to 112. So we're talking about negative 112 divided by 2 times negative 16. So in my calculator, because I don't expect you to do this in your head, that would be 112 divided by 32. So about 3.5 seconds. Now, I said seconds, but didn't even think about how I wrote x equals, but it's really the time axis. So at 3.5 seconds is the x value that it gets to the maximum height. So that's the time it takes, 3.5 seconds. And what you need to do next is figure out what the maximum height is. So that's going back to that equation and typing in negative 16 times 3.5 squared, and then it was plus 112 times 3.5. So it gets up to 196 feet in the air. So what is the maximum height? It's 196 feet. And I went ahead and labeled those already. So algebraically determine the time when a rocket reaches the ground. There's actually a couple ways you can do this. Usually what I talk about it, well, if it starts at 0, it needs an end. And this only works if you're starting at the origin. If it takes 3.5 seconds to get up here, it also needs to take 3.5 seconds to get back to the Earth. Now that rule does not apply if we shifted up on the curve at all. So that trick does not always work. So I already know that my answer is 7 seconds. The other way of doing it is taking that equation, negative 16t squared plus 112t, and setting it equal to 0. And what you can do from here is factor out a t. And while you're at it, you could actually factor out another number, but I'm just going to factor out a t. And the only way to make this work is if this piece equals 0. Let me change colors one more time because I'm running out of room. Negative 16t plus 112 needs to equal 0. So I need to subtract 112 over. Well, 0 minus 112 is negative 112, and then divided by negative 16. gives me 7 seconds. So t is equal to then negative 112 divided by negative 16, and we get 7 seconds. And we already labeled it right there. So as we move on, we have a skateboard half pipe, and again, they give you the formula as you see it. X is the horizontal distance. We have a 20-foot wide half pipe, and Y represents the ramp's height above the ground. And it's asking you to use a graphing calculator to come up with this. So let's go ahead and do that. We have Y equals, so I hit the Y equals button right there, 0.06 x squared, x squared minus 1.2x, and then plus 7, and we want it to be 20 feet wide, so I'm just guessing here, I want my window to go from 0 to 20, and let's just see what that graph looks like first. Well, that looks pretty good. So I think from here you can pretty much tell what's happening, but if not, what you could also do is change your window to go from 0 to 7, and I hope that makes sense. So it goes from 0 to 7. Well, that doesn't look nearly as nice because I zoomed in quite a bit. That looks like a scary half pipe for skateboarders. But anyway, we can see just about what the graph looks like by playing around with our calculator. And it looked like it started at 0.7. And that should make sense because if I plugged in 0 here and here, I would get a y-intercept of 7. And then over here at 20, x was 20, it looked like it was also 7. But you can also confirm what that number is by looking at the tables. Second table, let me scroll down quite a bit. Yeah, 27. And while I'm at it, you could actually figure out that the turning point is at x equals 10, 1. So as I go down and then come back up, it looks like we have this turning point at 10, 1. Height, its endpoints, its minimum point, I think we did it all. Now, you can confirm that those points are correct by doing formulas like x equals negative b over 2a. And you can figure out that the b value is negative 1.2, so the negative of that makes it positive, and then if you double that 0.06, the a value, you have 1.2 divided by 0.12, which, that equals 10. And then you can figure out what the ordered pair is by plugging in 10 in for all of those x's. Times 10 squared minus 1.2 times 10 plus 7, which is actually really nice because 10 squared is 100, so you move that decimal over twice, move the decimal over once, and you do get a y value of 1. So there's things that you could do in your head, but it's just made easier with a graphing calculator. And I think we've answered every question. Here's another modeling situation. The percentage of kernels that pop rises and then falls as the temperature of the oil, yada, yada, yada. But they give you the equation. So as you reread this, P represents the percent of kernels that pop, and T represents the temperature. So even if you don't understand all the words, you can kind of deduce from the problem what each one is. So if we algebraically, that means actually doing algebra, to find the highest percentage, well, that's going to happen at the vertex, at the turning point. So that's going to tell me to use my x equals negative b over 2a formula. And again, I use t because that's the independent variable. So negative of 2.8 divided by doubling that negative 1 over 250. And what I like so much about these calculators is I can actually just type it in that way. So alpha x, I already forgot what the number was, negative 2.8, and then double times the a value is another fraction, so another alpha x, -1/250. And this calculator will spit out what the correct answer is. So the temperature was 350, and I really don't care about the units, but they do say it's degrees Fahrenheit. So that's part of my answer, but then they also want you to figure out what's the p-value. So that's going back to the original problem and typing in -1/250, 350 squared plus 2.8 times 350. I'm just plugging in 350 in for all of those t's. And yeah, let me see if I can just squeeze that over. Squared, and then 2.8, and then lastly -394. So that's about 96%. So we always end up with kernels at the end. And if we use the calculator, we can actually sketch this curve. So I'm going to kind of cheat here. I'm going to pause the video and just... So I went to y equals and I typed that in. And now when I go to my window, it says just p-value is bigger than 0. And I don't know. Let me hit zoom 6 and see that nothing shows up. And the reason why nothing shows up is I have this y-intercept of -394. So I might change my window to just be 0 to 350. To go, and I'm going to hit zoom 0. That's going to fit it into my screen, and that only did the bottom half. So what I also need to do is change my window to get to 700 and go back to that graph. And because we want p-values bigger than 100, or sorry, bigger than 0, I actually can change my window and zoom in quite a bit. I don't know what these numbers are. Maybe I'll do 200 to 500. Oh, that was a lucky guess. And when I did that, I can actually get rid of these y values to be 0. And I might even be off just a little bit, but something like that. And what I could also do is go back to that. Maybe I'll change it to be, I don't know, 100 to 600. And just to get like a few negative numbers, like -20 in here. And the reason why I'm doing that is if I hit second trace, I can actually find the 0. It's the second option down. And I can move my cursor to the left and hit enter. And then to the right, hit enter. And then in between, hit enter a third time. And I can see that the 0 actually happens at 195 degrees. So 195 degrees. So that would be like right here. But then I need to do that again on the other side. Second trace, the second option, move my cursor to the right. I just need to be on the left side, hit enter, on the right side, hit enter, and then somewhere in between, and it's about 505 degrees. And so if we have 800 kernels and we expect to get the optimal temperature, that was at 350, getting 96%, all I would do is multiply that by 0.96 to get my optimal percent. So 800 times 0.96, so about 768 kernels. And I think I'm running out of time for my, here, let me pause and get you a good answer. So if we want 85%, I would need a equation in here, y equals 85, and with a graphing calculator, I'm looking for that point of intersection